Hi everyone, here we are with chapter 15 and it's on ionic bonding and ionic compounds. So some of it's going to be review. Some of it we already learned first semester. If you remember back in chapter 6 we learned how to write and name chemical compounds that are ionic. You remember the crisscross and Roman numerals and stuff like that. So we're going to go back and review that and then talk more about ionic compounds and their properties. So the first thing that I want to review is the term valence electrons. So we talked about valence electrons in the previous chapter. So if you remember, valence means the electrons in the outermost energy level, okay? And if you recall that the group number will basically tell you how many valence electrons there are in that particular element. So for an example, group 1 will have how many valence electrons? 1. Okay, so everything in group 1 will have 1 valence electron. So 1 electron in its outermost shell. So which group will have 2 valence electrons? So then that would be group 2, right? So let's write a 2 right there. And then group 3 has 3 valence electrons. Okay, so don't forget when you count your groups, we skip the transition metals. So 1, 2, skip the transition metals, and then 3 through 8. Let's start by talking about cations and reviewing what cations are. So what is the charge on cations? They are positive. And how do they get that positive charge? Well, they will have to lose electrons. So cations are going to lose electrons to obey what we call the octet rule. What does oct mean? Oct means 8, right? So which group of elements have 8 valence electrons? That would be your noble gases, correct? And so that means that your cations are going to lose electrons so that they can have 8 valence electrons like one of the noble gases. And then therefore their outermost S and P sublevels will be filled and they will be stable. All right, let's go ahead and fill in the blanks here. So let's follow our finger. Metallic atoms, okay, blank, electrons to obey the octet rule. So metallic atoms, the reason why it says metallic is because your cations, the ones that make positive charges, are metals, okay, metals, right? So they are going to lose electrons to obey the octet rule, and most of them lose between 1 and 3 electrons. And these metals, therefore, have a positive charge. Okay, so let's go on to the next slide. All right, anions. So what is the charge on anions? Anions have a negative charge, and how do they get that negative charge again? Well, they will have to gain electrons. Okay, and it says that, yes, anions gain electrons to obey the octet rule. Most of them gain between 1 and 3 electrons. Therefore, remember, they are the nonmetals, right? The anions are the nonmetals on the right-hand side of the stairs. So therefore, they have a negative charge because they are gaining electrons. All right, so the nonmetals have a negative charge. Now let's talk about the transition metals. So we know that the transition metals will form a positive charge, so they will form cations because they are metals, so they will lose electrons, but they have what we call a pseudo-noble gas configuration. So what does pseudo mean? Pseudo means like fake or false, okay? So they have what we call a fake noble gas configuration. Remember, your transition metals always do something different. Okay, they always do something different. And remember, your transition metals, they can also have what we call multiple charges. Many of them have more than one possible charge. So like iron can have a +2 or a +3 charge. Copper could be +1 or +2. So a lot of them have more than one possible charge. Remember, there are 3 transition metals that only have one possible charge that you need to remember. Remember, silver is always going to be +1. Zinc is always going to be +2. And cadmium is always going to be also +2. Okay, so they are They kind of make like that, like backwards L, you know, on your periodic table. So make sure you have those memorized. Those are the 3 transition metals with only 1 possible charge. Now that we have reviewed cations and anions, now we can talk about how they form ionic bonds. So remember, we have opposites attract, a positive charge and a negative charge. One loses electrons, all right? Cations lose electrons, anions gain electrons, right? So they are transferring their electrons in order to make a bond, and then therefore they will be stable. When we have opposites attract, this is a key term that you should know. Any type of like plus and a positive and a negative, like opposites attract, is referred to as an electrostatic force of attraction. Okay, so electrostatic force of attraction, that just means opposites attract. Don't forget, when you have your ionic compounds or your ionic bonds that are coming together, they are neutral. Okay, no charge. That's why we did the crisscross, to balance out the charges so that your compounds will equal 0. Okay, so the negative charges have to equal the positive charges so that overall the equals 0. And that's how we make our ionic compounds. All right, so once they are neutral, then you know that the electrons lost will equal the electrons gained. All right, and that's just because of the law of conservation. So then let's do a quick example for review. So let's say we have aluminum being combined with oxygen. So look on your periodic table, find their charges. So aluminum is +3, oxygen is -2. Okay, so you can do crisscross. The 3 will come down there, the 2 will come down there, and then you can find their formula, right? Or you can look at 2 and 3. Okay, what's a common multiple of 2 and 3? 6. So that means in order to make the aluminum equal 6, this will need to be multiplied by 2. So I need 2 of those. And then in order for the oxygen to equal 6, I need to multiply that by 3, right? So you can see how crisscross is just like a shortcut method. But you should understand that you need to make sure that the charges have to equal out to equal 0 because the compound is neutral. And then don't forget, when you're naming your ionic compounds, the cations are always written first and the name does not change. So it is aluminum, and then the anion, we change the ending to "ide." So aluminum oxide. All right, so here are some properties of your ionic compounds. So at room temperature, they are crystalline solids at room temperature. And that is something that you have personal experience with. A generic term for ionic compound is salt. We call them salts. Okay, so salt, once again, is just a generic term to represent an ionic compound. So you have seen salt before. Like if you cook and you have salt in your house, you know that at room temperature, salt is a solid. And your ionic compounds, since they have opposites attract and that electrostatic force of attraction, it is a very, very strong bond, okay? They will make a very, very strong bond. Therefore, it's going to require a lot of energy to break those bonds. So your ionic compounds also have high melting points and also high boiling points. That is just indicating that it takes a lot of energy to break those bonds. And then something else that you need to know for this chapter, yes, your ionic compounds, they can conduct electricity, but they have to be in these 2 states of matter. They have to be in the molten state. Molten means melted. Okay, molten means melted. Or if they are water soluble. So if they can dissolve in water, they will also conduct electricity. So water soluble, meaning like they have to be able to dissolve in water, so that means aqueous. Okay, don't forget, aqueous just means dissolved in water. So this is what it kind of looks like on paper when they are in the molten state or if they are dissolved in water. So I'm going to take your common salt, sodium chloride. Okay, so S just means solid. And what happens when it becomes melted or when it dissolves in water, it will actually separate into its ions. Okay, it will actually separate into these charged particles. So you actually have the charged particles in solution, not in the solid form. All right, so remember the solid form here is neutral with no charge, but then when they melt or when they are dissolved in water, they separate into their ions. Now you have charged particles in solution. So when you have charged particles in solution, that is what allows it to conduct electricity. Okay, you have to have some type of charged particle in solution in order for electricity to be produced, and that's what happens. These are some salt structures, just some of them what they might look like, mostly on paper and stuff. This one here on the left, this is what we call a space-filled model. So a space-filled model will kind of give you an idea of how big the ions are and then how much space they will occupy. And then the one on the right is called a ball and stick model. Okay, the ball and stick model. And notice that they alternate, positive, negative, right? Positive, negative, they alternate in the structure. And it's very organized. And that's how it is a very strong structure, because they're completely surrounded by the opposite charge. Now, this is what happens to the salt structure when you dissolve it in water. Okay, so notice these water molecules here. Okay, water molecules, these are water molecules. They are attacking the ions. All right, they are attacking the ions. They basically pull the ions away from the structure. Okay, see how the water molecules are dragging the ions away from the structure. So that's why when it dissolves, it will only have Na plus in solution and Cl minus in solution. It's going to completely separate the entire model. Okay, to the point where all of the ions are like free flowing in solution. All right, and that's why it allows it to conduct electricity. Once again, you got charged particles floating around in solution. Okay, also in this chapter, we're going to talk about metallic bonding. So metallic, that's just a fancy word for metals. So this is the bonding that occurs in metals. All right, and let me show you a picture on the next slide. And it's going over this model right here. We refer to metallic bonding as the sea of electrons. Okay, sea of electrons. These electrons are freely moving. Well, this is what we also call mobile valence electrons. They're able to move around freely. Okay, they are not like combined or attached to any particular cation. So here we have a picture. When I pulled up this slide into this program, it's not allowing my little picture to show all the really cool things about it. But you see these black dots here? Okay, the black dots are electrons that are free flowing. So if this picture was working correctly, you would see these black dots just moving across the screen, okay, freely. These red circles represent cations, okay, cations from the metal. So like the positive charges here. And then you just have the black dots, which are the electrons, free flowing like the sea. And that's why we call it the sea of electrons, okay? So for an example, also your metals are in what we call a crystalline structure. So they also have a lattice structure for metals. And each lattice point is basically going to be a cation for that particular metal. And because of those mobile valence electrons, these are some great properties of metals that you need to be familiar with. All right? They are, yes, excellent conductors of electricity. So once again, in order to have electricity, you have to have a charged particle that is moving around freely. So in the case of a metal, it's the electrons. Okay, the electrons that are the charged particles that is allowing your metals to conduct electricity. And also it's good to know that your metals can conduct in the solid state, but ionic compounds cannot. Your metals are also what we say ductile. Ductile means that they could be drawn into wires. So we can put them like into a mold that makes wires, and it's because of the mobile valence electrons that allows them to manipulate themselves to take on different shapes. And then that leads us to that metals are malleable. So malleable means that they can be, we can make them into different shapes, okay, because of the mobile valence electrons. All right. And the last thing, and this is just some extra information about metals, there are these things called alloys. So alloys are a mixture of metals together. And so some people would ask me, well, if you have a metal and a non-metal, we know that that's ionic. And if you have two non-metals together, we know that's covalent. And then some students would ask me, well, what do you call it when you have two metals together? Well, two metals mixed together, we call them alloys. All right, and sometimes we would want to mix metals together to make them better and stronger and have better properties. So here are some examples of alloys that you have probably have or seen and you are familiar with. Stainless steel, sterling silver, 14 karat gold, brass and bronze. These are all examples of alloys. So obviously stainless steel, you use items that are made out of stainless steel probably every day, like your silverware and everything. So iron, it rusts very easily. And so if we mix it with some chromium and some carbon and some nickel, then it would not rust as easily. Let's talk about 14 karat gold. So does anybody know how many carats would be pure gold? Well, 24. 24 carats is like 100% pure gold. So 14 karat gold is a mixture. It contains a little bit of copper in there. And the reason why we don't usually make jewelry out of 24 karat gold is because it's too soft. It's too soft to hold the design. And plus, if you've ever seen 24 karat gold, it's very, very yellow. And so some people don't like their jewelry to look that yellow. And so we mix it with some other metals to get the desired hardness and the desired color for it. Even white gold is a mixture of, has some yellow gold inside the white gold. All right, so those are just some examples of alloys, and I think that is about it. All right, so that is everything for chapter 15, and we will do a lot more practice in class. All right, see you later. Bye.